Great, thank you. Yes, so I will be talking today about demonstrating the capabilities of state-of-the-art quantum systems. As an experimentalist, this is my way of sliding into QIP, and I'm going to be talking about um, kind of the intersection of theory and experiment and software, and how these are all coming together to push the boundaries of what we can do on near-term systems. So the focus of this talk is really going to be on answering this question: why should we do demonstrations on near-term devices when we know that they're noisy and we don't have error correction, and we haven't shown that we can do something useful yet? And I think the answer to this is really that we're trying to push towards being able to look at harder and harder problems and eventually get to that holy grail of quantum advantage. So there's a few different components to this that I'm going to talk about today, and how do we get to harder and harder problems. The first piece that I have highlighted here, I'm not really going to spend any time on, but I think it's important to note co-design of hardware and error correcting codes, or co-design of hardware and algorithms. The IBM Quantum theory group had some work last year where they developed new classes of error correcting codes, including this heavy hex code, which can be used on a sparser coupling map than the surface code, which requires a square lattice connectivity. And this was kind of to get around some of the obstacles of having crosstalk on a highly connected device. So this coming together of the theory and the hardware allowed us to find a solution from the error correction side. And I think this co-design of hardware and algorithms is going to continue to be important going forward. The next component here, I think, is fairly obvious, that doing demonstrations allows us to measure progress and prove that we are making progress on our devices and our full stack, really. So I'll talk a little bit about this and focus on one specific example. And then all of these are building towards how do we develop new tools that are going to help us in this near-term regime where we need things like error mitigation, because we can't do error correction yet. So in particular, I'm going to mention bringing in classical resources to augment the power of our quantum systems. So starting with benchmarking. If you've seen an IBM talk in the past couple of years, you've heard us talk about quantum volume, and other groups have started measuring quantum volume on their systems. This is a metric which is a holistic measure of our quantum system performance. So it takes into account error rates on the gates and the measurements, connectivity, your gate set. We measure quantum volume by looking at random circuits that have this structure, where we're looking at circuits that have the same width or number of qubits as depth, so square circuits, and they have this structure of basically random SU4 gates between different pairs of qubits in each layer. And we determine the success of these circuits by looking at the output distribution that comes from averaging over many of these circuits and comparing each one of those to its ideal output, which we can find by a classical simulation. And we compare those using what's called the heavy output, and is defined here. So over the past couple of years that we've been measuring quantum volume, we've seen progress in this number coming up. And each step in quantum volume marks kind of a significant improvement, because it's kind of it's this coarse grained metric where you have to go up in one layer at each point. So we've seen improvements come from better and better devices. We've also seen on the same device that we've been able to improve quantum volume through things like better gate calibration, incorporating dynamical decoupling techniques, and improved compiler efficiencies. So some of these things are outlined in this paper here. Of course, quantum volume, we're looking at some subset of the qubits on our whole device, and we have devices of 27 qubits, 65 qubits. When we have tens of qubits and we can't, we don't have the error rates to do very long depth circuits yet. We want other metrics that can kind of capture the performance across the device. And one thing that we're always interested in is measuring entanglement across our devices. As we get to a larger number of qubits, the metric for entanglement becomes, we have to think of clever ways to measure the whole device. So one that we've used in the past couple of years is the measuring GHZ state fidelity using multiple quantum coherence. So this is a technique that we borrow from the quantum sensing community, where we prepare a GHZ state, apply a phase to all the qubits in the GHZ state, and then unentangle, reverse the GHZ circuit. And at the end, we've encoded this phase back onto the control qubit here. And by analyzing the state of the control qubit as a function of this phase, we can extract bounds on the fidelity of the GHZ. And when we first looked at this on a device that was a couple years old, IBM Q Johannesburg, which was a 20 qubit device and has since been retired, we were able to show entanglement of up to 18 qubits on that device. And just recently, the University of Melbourne group used the same methods with a focus on measurement, error mitigation, and clever circuit construction, and showed that they could entangle all 27 qubits on this newer device, IBM Q Montreal, which is the same device that we've tested our highest quantum volume on. So we kind of confirm with these different metrics that we're really making progress on the whole system. Now, other benchmarks, as we're getting into this regime of tens of qubits, where we might want to look at something harder, but we can't just run Shor's algorithm or Grover's algorithm and prove to people that everything's working right. There's historically been different tests. These are kind of tests of quantumness that have served as benchmarks of quantum hardware. So a Bell's test or CHSH test. And more recently, there's been proofs from Bravi et al. On that show that we can have a quantum advantage in kind of a restricted framework. Here, this was looking at constant depth circuits. So the kind of tests of quantumness that are available to us now are kind of looking at some kind of limited space where we can prove that there is that our quantum system can do something beyond what a classical system could do. So we had some work on this in the past year, where we were looking at a different kind of dimension of restricting the problem that we're looking at. So in particular, we looked at what we called restricted space computations, where the framework is that we have some number of input bits which are treated as read-only memory, and only a single bit where that can be used for computation. So in the quantum circuit, this looks like some gates that are all single qubit operations on one output bit that are controlled by a single qubit on the input register. So in this framework, we can compute arbitrary Boolean functions with a quantum computer. But classically, there are many that can only be computed approximately. And before I move on, I'll mention that Dmitry Maslov, first author on this paper, is going to be talking about this in more detail in a session tomorrow. So specifically, the functions that we're looking at are symmetric functions that are not computable classically. So symmetric functions are defined as functions where the output only depends on the Hamming weight of the input. And these functions can be computed by a quantum circuit with order n squared entangling gates with this one single qubit of computational space. And in fact, a perfect quantum computer would be able to do this perfectly, but we have noisy systems. So what we wanted to look at was, can we beat the classical thresholds for computing these functions? So the simplest function to look at in this class is the second least significant bit function, which is just like it sounds. It's defined as the value of the second least significant bit of the input weight. And a special case of this function is SLSB3, where there are 3 input bits. This is equivalent to the majority function. And in the paper, we work out for n bits what the classical threshold would be. So our test of quantum advantage in this restricted space is whether we can compute these functions on our quantum system with a higher success rate than these thresholds. So Dimitri's talk will go into how we find the circuits to compute each of these functions. But I want to highlight that there's two tools that we really incorporated into this demonstration. One was the use of quantum signal processing to find circuits that would do the SLSB3 function. So quantum signal processing is a scalable method which we can use to compute any symmetric Boolean function, and it gives a loose bound on the number of gates needed to compute these functions. So we found n squared 2 qubit gates and order n single qubit gates. For this SLSB function, we found it's a special case where we can actually further optimize the circuits so that we can make use of a structure that looks like this and actually compute these functions with 2n-1 entangling gates. So the quantum signal processing is still useful going to larger systems or to other Boolean functions where we don't have this special additional optimization we can do. And the second tool that we incorporated is that we had to use custom gates in order to implement these circuits. So anyone who's played around with our devices running through Qiskit, that we have a C0 gate available. And these gates here in the circuit are locally equivalent to a square root C0. So we actually use Qiskit pulse functionality to calibrate up the square root C0 and incorporate that into these circuits and run everything through Qiskit pulse. So the results are that we were able to run this on up to 6 input bits on one of our 27 qubit devices, IBM Q Berlin. And we see that we're above the threshold for all of these cases for beating the classical limit. So, as I said, this is a restricted model, but it allows us to benchmark these kind of small numbers of qubits, and I think gives us a direction to keep looking for quantum advantage in different spaces and kind of expand the area where we have provable quantum advantages. So I've already kind of started talking about how in our demonstrations, we're really thinking about what new tools are we developing and how can we build upon them. And I'm gonna get into that a bit more here and talk a lot about how we're incorporating or relying on classical resources to help expand what we can do in our near-term hardware. So the best example of this is with error mitigation, which I think we've heard about in talks throughout this week about how important error mitigation is in this era before we have quantum error correction. And these techniques rely on being able to do some classical post-processing of our data to find a mitigated expectation value. So our first demonstration of using error mitigation was a couple years ago looking at gate error mitigation. So in this case, we're trying to reduce the effect of incoherent noise on our circuit. So this works by taking a circuit like the one on the top, which is written out in terms of microwave pulses representing our gates, where we would run this circuit and then measure our expectation values at the end. And then we would take the same circuit and stretch it out so that all of the gates are slower. So each gate still performs the same rotation. It should be the same unitary if there was no noise, but it's slowed down. So effectively, this bottom circuit sees more T1 than the top circuit. And we can take those 2 points and extrapolate the expectation values down to the point where these gates have 0 duration and we have 0 effective T1. And this work showed that we could use this extrapolation method to improve the accuracy of applications like finding the ground state energy of small molecules. And in principle, we can use this going forward to go to harder problems. Now, on the other side here, we have measurement errors, which also we need to think about how do we mitigate measurement errors. And while we have a classical processing step here where we have to do the extrapolation, on the measurement side, we found that the classical post-processing step is very intensive. So I'm going to walk through this example in a little bit more detail. So the problem here is that at the end of an experiment, our system is in some state rho, and we model the measurement as an ideal measurement, which gives us outcomes X that are acted upon by some classical noise channel, so that in the end we detect outcomes Y. Now, if we have a system of 20 qubits or more, and our measurement errors are what we would still consider small, sub 1%, on a large enough system, our results are still going to be washed out by that measurement error. So we really need to find a way to kind of invert this process and find the ideal measurement outcomes. So we can model this classical noise channel as a matrix of transition probabilities. But we need to know, how do we find A and how do we find these ideal measurement outcomes? And what we've done in the past in our first chemistry paper from 2017 is one of these methods where we calibrate a full transition matrix A, and we either take a matrix inverse or we do some linear least squares minimization to solve for the ideal outcomes. And as you can imagine, this is very computationally intensive. These things scale as to the n for n qubits, as well as the calibration step scaling as 2 to the n. So this is not an approach that's going to work for very long. So to going back to the calibration part, just to find that matrix A, if we wanted to do a full calibration, we would do this by preparing all possible input states, and then constructing these matrix elements of all the possible outcomes of those to the end state preparations. So clearly this is only practical for small devices. And what we looked at in our work is trying to not mitigate on the actual shot vector that comes out here, but to try to find mitigated expectation values, because that's what we're really after in all of these experiments. It really only makes sense to talk about mitigated mean values. So now the question is not how do we find those X outcomes, but how do we find a mitigated mean value, which is an unbiased estimator of our expectation value. And our proposal was to model the noise as a continuous time Markov process. And this looks like A being defined as the exponent of a generator matrix, which is constructed out of out of these atomic generators and transitions that we can calibrate the transition rates for. This has the advantage of being, this is classically, the inverse of this is classically simulatable. We can to take the inverse of this, is just the exponent of -g, and this is efficient to implement the noise inversion step. And additionally, we can decide what transitions we want to include. So if we don't think there's much correlated noise, then we only include single qubit transitions, or we can add in additional transitions depending on what our noise model is. The actual process of doing this mitigation is to sample. We can efficiently find this inverse A matrix as a sum of stochastic matrices with some coefficients. And what this error mitigation process looks like is a sampling from all of our shots, and then sampling from these stochastic matrices, and then applying that matrix to our shot vector, and sampling from the outputs and updating our mitigated value. An important point here is that we can kind of define a noise strength parameter, gamma, which is kind of related to the maximum transition rates that would be in this inverse matrix. And this noise strength defines how bad our variance is, and that tells us how many shots we need in order to compute mitigated mean values. So the important point here, and I know I'm going through this pretty quickly, but the important point is that now our scaling is with the number of shots instead of the number of qubits, which is actually much easier for us to increase the shots in the experiment versus having a very computationally intensive post-processing step that depends on the number of an exponential scaling of the number of qubits. To dive into the details more, I encourage you to check out this paper. There's similar work from this group here. We tested this on some large circuits, like preparing graph states on up to 12 qubits. And we found that this method works beyond where we could mitigate with one of the older methods of calibrating a full A matrix. And we could use this on up to 20 qubits, which was the maximum we had available at the time. So this is a method that's really gonna carry us forward in being able to do these hard look at expectation values, which is a lot of what we're looking at on near-term applications and algorithms on devices of tens to hundreds of qubits. So all of these tools that we've been building up, like I said in the beginning, the goal is to get to harder problems. And I just want to briefly mention two experiments that we've been working on very recently. One is iterative phase estimation, and this incorporates another tool which is mid-circuit measurement and feed forward, and allows us to do dynamic circuits where we have a classical processing step that happens in real time within the circuit. And that gives, obviously that's important for quantum error correction, but it also gives us a lot of flexibility in the near term. So I'll just highlight that. And then the last experiment I want to mention is just a teaser of something that we're working on now, which is trying to reduce the problem size of simulating a molecule on mini qubits by splitting up the problem into many smaller experiments. And we've been testing this on a water molecule where we've seen that we can encode 10 spin orbitals into 5 qubits. And I'm not telling you yet how we've done that, but that's something to look out for. And we've simulated this molecule with a number of geometries measuring the ground state energies. with fairly high accuracy, around 10 millihartry. So I'm close to my time limit here, so I just want to highlight that with each of these demonstrations that we've gone through, we're learning something new about the system. We're leveraging advances in the hardware as well as in the theory and software. And we want to use all of these techniques to keep pushing towards harder and harder problems that we can access. And I'll just flash this last slide to say that for people who are interested in working on some of these problems, we have an open science challenge out now, which is a competition to find one, the best swap gate, and two, the highest fidelity graph state. And there is a money prize there. So check that out if you're interested in, and if you're interested in other things like our researchers program for running stuff on our devices or for jobs and internships, please check out these links here too. So I will end there, and I'll be around for the roundtables for questions. Thank you.
Thanks a lot, Sarah, for your wonderful talk. So I guess we have now some minutes for questions. There is one from Ernesto Galbao here in the slide.
Sorry, I'm sorry, I didn't hear the question.
Here. I'm sorry. Yeah. So apparently our session chair, Maria, has some audio connectivity issues. So the question she wanted to ask is by Ernesto, and it's about the quantum volume. And the question is, because it requires classical simulation, what benchmark would you adopt to go beyond sort of the classically simulable regime, if I may paraphrase this?
Yeah, that's a good question. I mean, I think I think with quantum volume, there's some limit to how long we can simulate the ideal outcomes and be able to compare it to our hardware. But I think that limit's still pretty far out. We're at, we're able now to look at 7 qubits on a device. I think it's going to be some years before we're hitting that limit of, some tens of qubits in quantum volume. And at that point, I think we'll be doing things like looking at qubit encodings, you could imagine a volume on some kind of encoded qubits as well. There may be other things that you would be doing at that point, but I think the usefulness of quantum volume is going to carry through for some years still.
I see. So you think in the near term this will be a good metric, I guess, for
yeah, yes.
Yes. If I may ask a question about your challenge at the end, I was wondering what you mean exactly by finding the best swap gate.
Yeah, thanks. I rushed through this. So we have this challenge where there's two different pieces of it. The best swap gate is the goal is to show that you can make a swap gate from running through Qiskit Pulse or however, and swap gates on our system have to be done by compiling CNOTs right now. But you could imagine through better control techniques that you could produce something with a higher fidelity. So the goal here is to design a swap gate, some kind of implementation of it, and measure its fidelity with randomized benchmarking and show that you've got the highest fidelity of anyone in this competition.
Okay, I see. So it's to try to compile the best swap gate with the operations you have available.
Right. Yeah, I think you could incorporate control techniques, compiler techniques, whatever.
Yes.
Whatever.
Maybe we can. So Fernando has a question on the noise mitigation tool, the unitary measurement mitigation tools. So he's wondering whether these are available through your cloud access, or is this?
Yes, so I believe, so measurement mitigation is fully incorporated into Qiskit. There's Qiskit Ignis is the component that contains these kind of characterization and error mitigation methods. And this CTMP method is available there too.
That's great, yeah. And so I'm just asking questions from the slide. So Michael is asking about how the geometry of your devices affects the crosstalk in measurement errors.
That's a good question. I mean, we've definitely seen that. You know, I mentioned as we've gone from kind of more highly connected devices to lower connectivity to try to avoid effects of crosstalk. So crosstalk can come into the measurement just through, you know, crosstalk on the gates or crosstalk on the measurement itself. Those are both possibilities. I think we've seen that in the paper that we have on the measurement mitigation. We got some benefit from going to transition, looking at transitions between 2 qubits. It may be worth investigating going to more. But it's an important question, and I think these have improved with our devices, but as you go to smaller and smaller errors, even smaller crosstalk is still important.
Sorry, so perhaps I can ask one more question and then we should move on to the roundtables. So Andras is asking whether in readout error mitigation, you are actually mitigating readout errors or some combination of readout errors and initialization errors. I'm not sure whether this. Yeah.
Oh, yeah, that's a good question. They should be somewhat symmetric, I think, but it could be possible that when you're doing the calibration, you want to take care that you're not looking at initialization errors as well. But it's not something I've looked at with the CTMP method.
Okay, thank you very much. So let's thank all the speakers and also the session chair, Maria, again. Unfortunately, yeah, these connectivity issues apparently persist. So now I would like to remind everyone that you can go to the roundtables to talk to the speakers by pushing the button at the bottom of your screen. And the speakers should stay here. We will give you the Zoom links to go there directly. Also, I should remind the audience that in 30 minutes, there will be the group photo opportunity. So we'll try to assemble a conference photo. So it'd be great if you could join that. Okay, so that's it for this business session. And we will now move to the roundtables. Thank you.